Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a deep dive into the TI-84 Plus, specifically looking at graphing and functions. This is going to be the first in a three-part series this fall. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Today we're really lucky to be joined by our two panelists, Karen Camp and David Sword. Karen was instructor of math education at Yale for 15 years and previously taught high school and middle school math for 13 years. She's been a T-Cube national instructor since 1998 and has been an author of materials for summer workshops and TI instructional websites. Karen speaks often on how to use technology effectively to enhance student understanding. Karen, thanks so much for being with us tonight.
Very excited for the webinar, Mike.
And Dave is a math consultant for Wayne Regional Educational Service Agency in Wayne County, Michigan. He's trained and deployed math coaches in priority schools, planned and delivered professional development, and provides support to school districts and public school academies in implementing local, statewide, and national initiatives. Previously a high school math teacher, Dave has been a part of several writing teams and projects for Texas Instruments. Dave, thanks for joining us tonight.
Thanks for having me.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send questions to Karen or Dave using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. And when you send those general messages, I don't know if you can see the screen right now, there's a red arrow pointing to all participants in the chat window. That's the best way to send your chats, again, to all participants, please. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance, as well as a link for the documents that are being used tonight at the conclusion of the webinar. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the WebEx menu and choose Audio Broadcast. At this point, Karen is going to discuss our agenda.
We're so glad for you to join us tonight. We're going to have a deep dive into advanced graphing capabilities of the TI-84 Plus technology and how you can use your TI-84 Plus CE and the rest of the family as a tool for inquiry. Dave and I are going to share several activities using linear, quadratic, polynomial, rational, and piecewise functions. You'll learn about the power of split-screen multiple representations, and we'll discuss strategies for questioning that foster inquiry and talk about how to summarize inquiry learning experiences to make it stick for your students.
Thanks so much, Karen. And Dave is going to discuss our expected outcomes for tonight.
We're going to really focus on analyzing and interpreting graphs. We're going to talk about linking multiple representations using tables. We're going to talk about using graph styles to explore function families and piecewise functions. And the focus of all of these is on student understanding. It's not just about pushing buttons, but about student learning. So we're looking forward to it.
Dave, thanks so much. Karen, it's all yours. Feel free to share your screen.
Okay, so first of all, we have tons of great ideas to share with you tonight. Don't worry if you can't catch them all. You can watch this webinar later on demand, and all of the activities will be in the associated documents. We're going to begin with our SmartView emulator, and my first activity is going to be about examining graphs of power functions and what are some of the patterns we might see. First, a teacher tip. Your SmartView emulator has actually 3 emulators all in one. And so if you're working in a classroom and you want to work back and forth, you might set up your C emulator instead of your CE because most of the features are the same. There are a couple that are different, but for this we're going to use our C. So I might begin with a pretty standard window. And one of the things that I use to help encourage students to visualize things is to turn on the grid. And when we turn on, whoops, that did not work. Sorry, second format, turn on the grid line. I forgot to press enter. And when you look at the graph, what you're going to notice about these grid lines is that they make very obvious that we are not dealing with a square window. The distances between the tick marks on the x-axis and the y-axis are different. And so I'm going to change to the zoom decimal window. It's one of several square windows, and it helps students to visualize exactly what they're looking at. Perpendicular lines will look perpendicular, and if you're working with Algebra 1 students, you can have them count boxes for slope, etc. Now, this window is relatively small. It starts at negative 6.6 for x and positive 6.6. If you decide that you need a different window, use multiples of this window, and it'll continue to give you friendly tracing increments and table increments. Okay, but we're going to begin with this window, and what we want to look at is we want to take a look at power functions. So what do I mean? I mean x squared, x to the 4th. I'm going to begin with the even-powered functions, x to the 6th. And when I give this graph to students or have students take a look at this graph, I want to ask them what do they notice. And I want to give them some thinking time and some writing time to write down some rough draft thinking because it helps them to engage in the activity and not just watch me do it. Also, teachers have found that if you tell them what you want them to notice, you might miss some interesting things that they are noticing. They might have you taking a scenic route through some interesting math instead of the direct route you have planned. They're both productive routes, and so there's a lot of different things that you might want to ask them. So I asked my students, what do you notice? And my students said that the higher powers had steeper sides, and we wanted to know what the y values were doing to make this happen. So what we're going to do is we're going to take a look at a table. And what we can do on the table here is I'm going to set the table to ask for the independent variable instead of automatically giving it to us. So when we look at this table, it's blank. But if I begin and we put in the number 1, we can see that all 3 have the number 1, number 2, number 3, number 4. We can see that the higher powers are getting steeper, faster, they're growing faster. We can also zoom in on the table, on the graph, and investigate what's going on right in here between 0 and 1. And so zooming in, if you start by selecting zoom in and press enter, the cursor is right now at 0, 0. It's going to zoom us right in there. And what's interesting here is that the higher powers are actually flatter when you zoom in. And we can check that out in our table. We can take a look at what happens if we put in 0.5. What happens if we put in 0.7? Okay, and so the higher powers actually are smaller. You can even put in fractions into the table. Since I'm in the C version, I go to alpha y equals to get my fraction template, and I'm going to put in 1/2 or 1/3. And again, we can take a look at what's happening. Why are these numbers getting smaller? Why do we get flatter graphs closer to the origin? All very productive ideas for inquiry. Then, of course, we want to also investigate our odd powers. So we're going to take a look at what happens when we look at x to the 3rd, 5th, and 7th. And students would hopefully notice some of the same behavior. Just one thing I want to mention here, I could go right back to zoom decimal, but if you had a window you were working with, you can go to zoom memory and choose number 1, zoom previous. Okay, and again, we can zoom in if we wanted to and see the flatter behavior right around the origin and the steeper behavior outside of the origin, and hopefully students are going to notice that the odd-powered functions act differently. They start negative and end positive, and finally we can second insert negative signs and see what happens when we have negative leading coefficients and how does this affect the end behavior. Okay, so you may be thinking this is really great, but I really want my students to be able to know this without a calculator, and I agree. We're here using the calculator and the graphical environment and the table numeric environment to build their understanding. There are going to be skills that you want your students to know and be able to do without without the calculator, but the learning experience will happen with the calculator. Okay, before we go to our second activity, I just want to give you a little bit of an overview. I know this is a busy slide, lots on it, but let's talk about how we can use the TI-84 as a tool for inquiry. You can include open-ended questions with your activities. You can even give students scenarios without any questions to begin with. Ask them, what might you want to know about this scenario, or tell me 3 things that you do know. You saw in the very brief power functions, we capitalized on multiple representations. We took a look at a graph, and we also took a look at a table. While you're capitalizing on multiple representations, try to begin with different representations. Maybe begin with algebra, begin with a graph. Don't always do it in the same order. Have students actively engaging with this scenario. We want them to do the math, not just view the math. I insist that my students have a written record of their rough draft notes and ideas. This could be on a whiteboard, it could be on a dry erase board, it could be on scratch paper or in a notebook or on a paper handout, but they have to be noting down what they're thinking. Speaking of thinking, very important, give students thinking time, and then don't steal another student's opportunity to think by talking too soon. Last 2 points, we want to encourage our students to reflect on connections and the mathematical meaning of the work they're doing, and at the end of the learning episode, we want to summarize their learning to make it stick. We will come back to that later. Let's go back to our TI-84 emulator. I'm going to now switch to the CE emulator. The other stuff is still back there. And I got very interested in all of the activities surrounding quadratic functions. Standard form, factored form, vertex form, and what were the connections that we could make there. So this activity that you're going to find in your associated documents has lots of parts. You can do these in different modules. You might do some for the students to do, or you might do them as a large class discussion. But I'm going to take you through some highlights of what the calculator can do to really explore these ideas. So I'm going to begin with y equals x squared minus 5x plus 4, an equation that I'm sure all of us can sit here and graph. I'm already in my Zoom decimal window. Let's see if I have my grid lines on. I do. And the first question I would ask students is, what questions could be asked about this graph? And hopefully students might want to know, where does it cross the x-axis, where does it cross the y-axis? And this first part of the activity is, what does the standard form have to do with the factored form? And we want students to put in the factored form. And some students might say, okay, I know it crosses the x-axis at +1 and +4, so they might guess that it's going to be x plus 1 and x plus 4. And I'm showing you this on purpose, but the way that students can connect their factored form to standard form is to use the tracer ball graph style. You'll notice that I arrowed all the way to the left. I press enter. I can change the color if I want, but I want to go arrow down to the line and change the line style by right arrowing to this tracer ball. You have to hit enter on OK or you will lose this, but watch what happens when you trace my supposed factoring. Ooh, that's a very interesting graph. It looks like mine, but it's in the wrong place, and the reason is because we have to change this to the negatives, and now you're going to see that the tracer ball is going to follow the previous graph. So this is a nice way as students are learning factoring to get a graphical representation of it and also see whether their graph was correct. I have it shut off right now, but I'm going to open up this view cube. Let me just make my window a little bit bigger. What this does here is it shows several parts of our graphing emulator. So you can put in the window, you can have the equations and the table all at the same time and have a multiple representation screen going on here. Okay, I'm going to continue with the graph. I've made the other ones kind of small, not that important for what I'm about to do. The last part of factored form and standard form is, what about these individual factors? What would happen if I put the individual factors in as separate functions? And I would give students a chance to think about this, maybe make a prediction, and then review the graph. And I found this so interesting to think about how the two linear factors multiply to equal the quadratic function. I asked students to think about, why do these functions have points in common? And let me just turn off y2. Remember that you can deactivate an equation without deleting it by pressing enter on the equal sign. And let's take a look at the table. Since the two linear functions in y3 and y4 multiply to equal the quadratic function, the table shows that we can take the 2 times the -1 to equal -2, or -2 times -5 to equal 10. So it's very powerful for students to think about the components of the quadratic form. Okay, moving right along, the second activity in quadratic functions, I wanted to think about, what about the symmetry in a parabola? So I'm going to change this one to x squared plus 6x plus 5. I'm going to get rid of this other stuff. And what I want to do is I want to take a look at this parabola in the table, and I'm going to begin with -7 in my table. And when I do second table, whoops, my table set did not work. Oh, I know why. It's because I'm still in independent ask and not auto. So I'm going to put that back to auto, and now my table will populate. And in the handout that the students are working on, they will actually write down this list of values on their handout. Is it busy work that I'm asking the students to do? No. Actually, by writing it down, I thought they're going to notice that there are several x values that have pairs of x values that have the same y value. So they're going to be asked to find a pair of x values that have the same y value and find their midpoint, or find the average. Let's take a look at the graph while we're looking at the table. Here is that graph. I'm going to actually double my y min and y max so I can see a little bit more of this. I don't have to double it, but it's a good amount. And we might have noticed that in my table, I had 2 points that had a y value of 5, or 2 points that had a y value of -3. Okay, so that tracer ball on there. Tracer ball takes a little bit longer to get the graph going because it's drawing those pixels. But we want students to draw some horizontal lines and see what they see. And the y3 is in black. That makes it a little bit hard to see. Let's change that color. Oops, it didn't work because I didn't press enter. Okay, so here are some horizontal lines for students to think about. What they're noticing here is that the horizontal line will hit their parabola, intersect it in 2 places, and these 2 values, if we find their average is going to give them the x value of the vertex. In this case, it's -3. We want to focus in on that average. I'm just going to turn this back to regular graphing. And what I'm going to do is I want to draw a vertical line in for my axis of symmetry. So I do second draw. Actually, I want to do this from the home screen, but second draw. I'm sorry, let me not do it from the home screen. Two ways to do it. Second draw from the graph screen. If you put in vertical, you can move to where you think it goes, like that. There we go. And this style indicator is what is asking me to press my graph button, and I can change the color if I like. So doing this from the graphing screen really gives you a lot of power over it. And this part of the activity is going to, again, have students notice symmetry and notice what happens if you find the average of these x values. We can go back to our home screen. So the x values for the roots or the zeros were -1 and -5. And so let's find their average. -1 plus -5. This is sort of the on-the-fly average. And don't forget about fractions are your friends. The fraction template, you don't need parentheses as grouping symbols if you use the fraction template. Okay, and the activity then prompts the students to think about how are you going to find the y value of the vertex, and there's a little bit more involved in that. The last two bits of this activity with quadratics have to do with vertex form, and I became really struck by a visual representation of where the vertex is with respect to the axis of symmetry. So let's go back here and let me clear some things out. Trying to get this back to where it was before. Okay, and now I want to put into y1, I want to put in x squared plus 2x minus 3. And I'm going to go back to my Zoom decimal. And what I see here is I've got a vertex at -1, -4. So students are asked to put that into vertex form. So it's x plus 1 squared minus 4, and the red graph is going to overlay onto the blue graph. Let's also draw in our vertical line, our axis of symmetry. Okay, and I love the green ones. Okay, so here is our picture. And what I want you to notice is that the axis of symmetry is at -1, and my two roots are symmetrically around that axis of symmetry, and they're exactly 2 units away. Let's take a look at what this looks like when we look at vertex form. Okay, so I took vertex form, and students had to set that vertex form equal to 0, solve using inverse operations, not forgetting the plus or minus, and they find out that the two values of x, where y equals 0, are at the points -1 plus or minus 2. Now those two values are at 1 and 3. We can see them right here on our graph, 1 and 3. But looking at it this way allows the students to make that connection that the -1 is the axis of symmetry and the plus or minus 2 is 2 units to the right and 2 units to the left. That in and of itself is pretty powerful, but what really blew my mind is that this technique allows us to visualize complex roots of situations where the quadratic does not intersect the x-axis. So let's change this up and let's talk about the quadratic. Let's do -2x, I think -2x, yep, plus 5. Okay, I'm going to just turn this one off right now. Here is my graph, and you can see it's really off the top of the screen, so I do need to change my y max to deal with this. So I can keep a square aspect ratio if I use that same 8.2 distance. Okay, so there is my graph. And what we can do with this is the vertex is at 1, 4. And so I'm going to now edit this vertex form from before, x minus 1 plus 4. And there's that vertex form. What I want to do is I actually want to think about what would happen if I took this vertex form, this parabola, and I flipped it upside down. And what would I have to do to vertex form to make it flip upside down, to reflect it over its own vertex? The vertex will stay the same, but the leading coefficient will have to be negative. So I simply have to insert a negative here. And I think that there's a lot of productive inquiry with students figuring out what they would have to make negative. Do you make the whole function negative? Is the whole function opposite? Or are there certain things that you have to do? But this is what needs to be done, is to just make that vertex, the A value negative, use vertex form, leave the vertex alone. Let's again draw in our vertical line. And the vertical line is going to be here at 1. And let's do green for visibility. Okay, and so, whoops, I think I just have to push enter to get that vertical line to stay. There we go. So what's going on here is the roots of the reflected parabola, the zeros are at 2 and negative 1. And if we were to look at vertex form of the original parabola, I didn't have the algebra done up, but the algebra works out to negative 1 plus or minus 2i. So vertex form was going to give us negative 1 plus or minus 2i. And so what does that mean? I'm sorry, it's positive 1 plus or minus 2i. And that positive 1 plus or minus 2i is, the positive 1 is here, and it's plus or minus 2 units. So the reflected parabola essentially gives a shortcut to the roots of the original parabola that doesn't actually touch the x-axis. This also works with values that have irrational parts, and you can read more about that in the associated document that is all done out. What I want to do is I actually want to point out a few of the questioning techniques that I did in these activities, and then I have one more quick mention before I pass the ball to Dave for him to carry on. So let's quickly look at a few more things. Some of the questions that are in these activities that you can ask students. You can ask them, what do you observe? You can ask them to generate questions that could be asked about a particular graph, table, or diagram. What more information do you want to know? What changes? What stays the same? Or what is in common with two parts, or what is different? Can you explain what you see or what you understand to a classmate or younger student? Can you convince me of something? What will happen if, and when will something be true? Okay, my last little activity is having to do with rational functions. Rational functions are functions that are created with fractions. And so if I take a fraction, a shortcut for the fraction template on the CE is to hit alpha x. If I take this rational function, x squared minus 3x plus 2, easily factored, all over x minus 2. I'm going to go back to my Zoom decimal window. And you'll notice that on the zoom decimal window, you will be able to visualize holes in the graph. Really powerful for students to see that. Now, when you factor this out, students are going to see that the remaining function, if you simplify it, is x minus 1. Let's go and use tracer ball style for that. And the question is, how is simplified form different from the rational form? And the simplified form, I never got that tracer style. You can see that one of the things with changing the graph style that I am forgetting is to go down and hit OK. Okay, so here's the blue graph with the hole, and the red graph is going to fill that hole. So the simplified form has a different domain than the original one. The last thing I want to show you with rational functions, besides just simplifying them and viewing holes and asymptotes, is that there's a lot of power that you can do by separating the parts of the rational function. What I'm going to do, I stored some things earlier. It's called a graph database. It's just a way for me to quickly pull up something that I stored for you earlier. Let's take a look at these two functions and their rational equation. Okay, so first of all, 2x squared minus 8, x squared minus 16. Let's take a look at those on the graph. I would ask students to pay attention to where they cross the x-axis, where they cross the y-axis. And if I want to view them as a quotient, I can put in the y1 and the y3. I accessed those from alpha trace. It's another shortcut. Alpha trace gives you the y variables, so you can enter those into your function y equals. And when you look at this rational function, a lot of great power is going on. The numerator function in blue, where the numerator equals 0, is where the rational function equals 0. The denominator function is in black. We have asymptotes for the rational function when the denominator function equals 0. And there's another neat inquiry that students can do around the y-intercepts, which I never thought about until I did this activity. So that's a very quick mention, and the full activity is in the associated documents. So just before Dave goes on, I just want to talk very, very quickly about inquiry doesn't mean letting students just explore and never coming back as a teacher and summarizing what you're doing. So there's a lot of cognitive science research that's been done about how to make it stick, and really important is to have students reflect on their work, practice self-explanations that they know what they're doing, and summarize the important results in writing after the learning activity. Either the teacher can do it or the students can do it, but this marks that activity, this math learning, as important math knowledge for students, and it's not just that fun thing that we did with the calculator. Okay, let me pass the ball to Dave, and he's going to carry on with a few more activities.
Good evening, TQ or TI participants. Thank you for sharing your evenings with us. What I would like to do is continue our conversation by looking at additional ways that we can empower students to explore connections between multiple representations. Specifically, I want to start with a function, a typical cubic function, x cubed minus 3x plus 1. I'm going to hit graph, and what I chose to do is just to show you a different view, and that is I chose the format here that has the grid dots, just so that you can see an alternate view of what Karen has shown you previously. But here's a typical function, and what we want is kids to be able to explore this, right? So if I hit trace, I can trace and see how the numbers change at the bottom of the screen. I can see that right in here it looks like there's a 0 near -2, so if I just press -2, enter, traces right to -2, and I can see that as I continue to trace and I look in the bottom right hand corner, I see that y changes sign as I get right near that x value, -1.9 and -1.8. I see something happening there. right? Well, that's a really rich environment, but it would be much nicer if kids could see this in a more powerful way. When I press mode, one of the options that I have available to me is a graph table split screen. So I'm going to select graph table split screen, and now when I press graph, I'm going to press zoom decimal again, because when I pressed the split screen, it changed the aspect ratio of my window. So to square it back up again, I pressed zoom decimal again to ensure that I have a square window and that when I trace on my X values, they will be decimals. And so now if I hit trace, I can still trace as I did before, but what's nice here is when I trace near X equals -2, I can see in the table over on the right, I can also get a much fuller view of what's happening numerically. And so it allows students to be able to explore that connection and to see that between -1.9 and -1.8, the Y values change sign. Really, really powerful. Now, what's nice about this as well is right now my control is in the graph side of the screen. I can shift my control over into the table side by just pressing second table or second graph. So now I'm over on the table side of the screen, and I can also trace in the table using the same kind of exploration that I did, but I can enhance that a little bit further by using the table functionalities. I can see here by the default, the step size is -1. Wouldn't it be nice if I could change that step size? Well, it's really nice here, but I'm even reminded up at the top of the screen that while I'm in the table side, all I have to do is press the addition key, and it allows me to change the step size. And I'll start here by zooming in with tenths. So when I zoom in here at tenths, I can continue my exploration again, and I see what I saw earlier between -1.9 and -1.8. I see a sign change over in the Y. And so what I would like to do is say, I wonder where between -1.9 and -1 8/10, where is the Y changing sign? Let me zoom in a little bit further. And I can change the step size now to hundredths. And similarly, I can continue this exploration and zoom in as far as I want. And it's a really, really rich, powerful way to allow students to be able to see multiple representations here of the information in the table, the information in the graph, and then when I go back to trace, I see the numerical representation as well. So here I see the 3 representations, opens up the door for students to have very, very rich exploration. Now, an additional exploration that we want students to be able to explore too, and we sort of leave this open-ended when we say, okay, we've already looked at what is happening in the neighborhood of the x-axis to locate the 0. What happens as the Y values increase toward a relative max? And I can see that as the x's are getting closer and closer to -1, I see the Y values are increasing until there's a maximum value of 3 that is reached. And so then I see the Y values start to decrease to the right of that. So again, the split screen opens up the door for the students to have a much, much richer exploration. So that's one activity. We call that zooming in on functions, using a graph table split screen to explore zeros and relative extremes with multiple representations. We have another activity that we'd like to share with you, and as Karen mentioned to you, I'm going to take advantage of the different emulator models. What I was just working with there was the TI-84 plus C. When I go to the TI-84 plus CE, all of the work that I had prepared in that version of the emulator is now preserved, and I'm ready to roll with the place where I'm at that point. So this
Dave,
next
can I just jump in real quick?
Of course.
You can also save an emulator state, meaning that you can save your emulator, all parts of it, and you can load that back up later. So there's ways that you can prepare that way as well.
Yep. So what are we going to do in this next activity? We're going to explore, again, a split screen environment, but we're going to explore it in a very enhanced way. What do I mean by that? I'm going to look at a function. I'm not even going to look at a function just yet. I'm going to set up a scatter plot that just has one point in it, the point 1, 1. You'll see why in just a moment. I've set this up to be a scatter plot. You can see that list 1, list 2 using the box. But what I'm going to do is I'm going to also go to the split screen mode, graph table mode, and zoom decimal. And I get a nice multiple representation again, where I have a scatter plot and a graph screen. And what I'm going to do at the same time is I'm going to hit zoom out one time. Karen talked about how you can change the values yourself and maintain an aspect ratio. One of the nice things about zoom out is if I zoom out right here and just press enter one time, it maintains the square window aspect ratio but gives me more space to explore, which is what this next investigation is going to be based on, is having a larger space available to me. And the nice thing about this right now is with this split screen like this and this scatter plot that's been set up on the right, this scatter plot is different than the table that we viewed in the previous example. The table in the previous example was built on a function. This is the data from the scatter plot. And when I press second table this time, again, it takes me over into the table and I can add more points. I can add 2, 5, or any point, -3, enter, and -7. But it enhances this environment where I can do more exploration. And so what we want to be able to do is, knowing now that this environment is accessible to me, what can I do with this and what can we have students do? One of the things that we're going to do is look at an investigation where students are given a scatter plot that is they can explore what is the mathematical relationship that defines that scatter plot, and then try to identify the rule that defines a related function. And to do that, what's nice is I can just write a very simple program, which I have written, called What's My Rule, and all that program is just 2 lines. In the first line, I used the sequence command to generate 11 ones. Why 11 ones? Because on this table right here, there are 11 slots that I can fill up. So I'm going to, in my program, I'm going to write, I'm going to generate these 11 ones, and I'm going to create what's called a locked list in L2, upon which this list is dependent on the data in list 1. And so you might ask, what is a locked list? Great question. I'm going to demonstrate that very briefly. A locked list is a way that I can create an interactive list. If I go into L3, for example, right now, and I just put, say, 1, 2, and 3. I just put 3, any number of elements in that list. I can go to L4. Many of you know this. I can take 2 times L3, and it will take everything in list 3 and multiply it by 2. The power of doing that formula is that I can get a calculation based on an entire list to show up in L4. The downside of that is once that calculation is done, now I'm at the heading of L4, that calculation that I had put in there is lost, okay? Now, what I can do is instead, I'm going to hit clear, and I'm going to clear out list 4, and I'm going to go to the top, and this time I'm going to use quotes, and I'm going to hit alpha, quote, 2, second, L3, the exact same thing that I typed before, but the quotes turns L4 into what we call a locked list. So now when I press enter, L4 is there, but you see at the top of the screen there is an icon that has a little lock there that tells me that this list is locked. What does that mean? When I go to the top, the formula is preserved. So I know what that formula is, and then number two, if I go back over to L3 and I add more data in there, L4 grows as L3 grows, and I can put anything I want in L3. I can put negative numbers in L3, and L4 grows and is dependent on L3. So that is what we mean by a locked list. It is a list that allows me to enter new data, and it maintains a current calculation. There is one caution that I need to know about a locked list, and that is, as long as that list definition is there, if L3 ever gets cleared for some reason, I will get an error message because L4 is dependent on L3. L4 is trying to do a calculation on L3. If L3 is cleared, L4 gives an error message. So that's a caution to be aware of. This is mentioned in the write-up for this activity. That's why I'm sort of saying it in passing here, but you can review that in the write-up of the activity afterwards. But as a reminder, that locked list needs to be cleared if I want to clear L3. The way to clear it is very simple. I go to the top, I press enter to enter into that list definition. When I press clear, it erases that locked list. The icon is gone at the top, okay? So that's what a locked list is. Now, how can I use a locked list in this activity? When I run the program, I'm going to run the program, what's my rule, and it might seem like something weird happens over on the right, and that is very simply that table now is populated with all of the values that I put in there, and I can come in, and as a student, we can say, students, there is a rule that defines the relationship between L1 and L2. The challenge for you is to find what that rule is. If a student comes in and changes this value here and makes it, say, a 2, they can say, oh, when x is 1, y is 3.5. When x is 2, y is 4. Let me see what y is when x is 0. When x is 0, I get a y-intercept of 3. It looks like this might be a linear function. So when I let x equal, let me try something farther away. Let me try x equals 6. When I get x equals 6, y is 6, and I get what appears to be a linear function. And so we can say to students, now that you think you might know what the rule is that defines this relationship, go to y equals and try to guess what it is. Or not guess, make a conjecture. I'm going to say, it looked to me like it had about a slope of 1/2. I'm just making a guess here. 1/2 x, I'm making an approximation, and I'll say, I think the y-intercept was 6. So when I press graph, oh, the y-intercept was 3. So I can fix it, and I can continue to try and identify the rule that defines the relationship. So that is a way to use an enhanced environment to explore a numerical relationship. What I've also done for you, and we've included it in the package, in this activity, if the student were to actually go over onto the table side and go to the top of L2, they can see the rule at the bottom of the page. What's nice is to rewrite this program so that it doesn't give away the answer. How did I do that? Well, I wrote what's my rule 2. It's not so easy to see here, but when I loaded that program into the TI Connect software, you can see here I cleared out all of my y equals so that there's nothing that's in the way. I turned off the plots. I set up scatter plot 1. I put the sequence into L1. I generated a random integer for A, B, and C from 1 to 5, and then I just put the equation A over B times L1 plus C, put that into L2, and it's a random linear function that when we run this program now, the students will get a random linear function that they have to identify the rule. And because you can edit this program, you don't have to make it a linear function. Let me go to y equals. Sorry, I should have cleared out that y equals. So now the student has the, I don't know if I think I ran the wrong program. What's my rule 2 is what I want to run, sorry. And what's my rule 2, you know, now notice has a different group of numbers. And again, the students can explore by trying to find, okay, let's find the y-intercept first. You don't tell them this, but of course they'll learn that finding the y-intercept is very nice. Then let me find another point, 3. And now I've got a reasonable estimate for what the slope is, for what the y-intercept is. When I go to y equals, I can enter an equation in. I'm just going to make a random attempt because I don't know what this equation is. Whoops. I'm going to hit 1/2 x plus 5. And wow, that was pretty cool. I got it on the first try. But so you can run this program as many times as you want, and each time it's going to generate new random integers for A, B, and C, and every time it's a new challenge for the students. So there's an example of using a locked list together with a program, together with a split screen environment where I have a graph, I have a table, I have a function, I have a function definition. So I'm really almost looking at 4 different representations because I have the scatter plot table, and then I have the discrete table from the scatter plot, the continuous table from the function. All right, so we have a few minutes remaining. What we wanted to do in the few minutes that remain was show you yet one more investigation, and that is an investigation that involves piecewise functions. And I'm going to use what Karen mentioned to you earlier, and that is I had saved my emulator state from previous work. And so I'm going to load that emulator state, and the emulator state that I want to load is this activity called piecewise parallelograms. What is this activity? Well, this is an activity that allows me to explore piecewise functions as it relates to a challenge of creating a graph that is a piecewise function that matches a parallelogram. Building this activity from scratch is also nice. How did we do this? I'm going to actually start from scratch and press second memory defaults and reset all of my defaults. What did that do? It turned off my plot and set my window back to standard settings and turned off my plot. I'm going to use a feature that is, I'm going to start with a square window, zoom. Oh, and also if you notice, it turned off the background here, the format of the dots that I had previously. If I want to turn those back on, all I do is go to second zoom, second format, and scroll down to the grid and make it either grid dot or grid line. I'm going to choose grid line, press enter, and when I press graph, I can see that my grid lines are there, and zoom decimal makes it a square window. One of the nice features that's accessible now in the TI-84 plus CE is a function called quick plot and fit EQ. What this does is it allows me to put points on the screen, and I'm going to go.
That's available in all of the TI-84 models, not just the CE. I'm sorry,
correct.
It's all available in both color models, pardon me, not the black.
Yep. So here I am at -1, I'm going to press enter. And then when I move over to -1 and press enter, and I go to 1, 4, and press enter. 1, 3, excuse me. Press enter, and then when I go to 4, 3 and press enter, I get the points that outline a parallelogram. And this soft key above y equals says fit EQ. If I press graph right now, one of the things that I can do is just tell this plot to plot the points only. And when I do that, by default, it asks me L1, L2, plot 1. I'm going to press OK, and there are my points. And the challenge that we give the students is, can you write a piecewise function that matches this parallelogram? What I've done is I've loaded the graphical database with 2 representations for that. Here's one, 2x, where x goes from -1 up to 1, and 2 for x goes from 1 to 4. But because it's turned off, I need to turn that on. And when I press graph, voila, I'm off. So let's go to x plus 1. And let's go to 3. And there we go. And so when I go to y equals, I can change the second one, which I know this is -1. And this, I believe, is 2x minus 5. And we get a second piecewise function. And so the final thing that I'll do before we start to wrap up is show you a second graphical database that shows a second representation that students could have come up with. Graphical databases are stored under the second draw menu. So if I go to second draw, I'm going to go to the store where it is recall is number 4. So I'll go down to number 4, recall graphical database number 2. And when I press enter, it will come up and show me that I could have represented this with 3 pieces, where the first piece is the 2 slanted pieces, if you will, and the other 2 pieces are just a single. You can do a piecewise function that just has 1 piece that's restricted over this domain, and you can see that the restrictions on the domains can be written either in shorthand notation like you saw in the previous example, or in the combined logic format where I include the and in the restriction definition. So here we have 3 pieces that define this parallelogram. Again, sorry, because those original points that I marked were not the target points, but you get the point. Ha! No pun intended there, accidental pun. I think with that then, that sort of gives the wrap up of these, and these write-ups are going to be provided for you, so we're just happy to make these available for you to be able to explore with your students afterwards. So I'm going to turn it back over to Mike. I'm going to pass the ball to Mike. I'm going to stop sharing my screen.
Dave, I'm going to help you out real quick.
Okay, sorry.
That's
sorry
okay.
about
Thanks. So to receive a certificate of attendance tonight, go ahead and click the link in the chat window. Also, this is a link for the documents that were used tonight by Karen and Dave. And I know a few people have been asking some questions throughout the webinar. Karen and Dave spent a lot of time on those documents, and they are very, very, very detailed. So I definitely think they're worth checking out. Some of your questions that you've asked tonight may even be answered by just looking at the documents they put together. If either of these links, for whatever reason, aren't working for you right this second, you'll automatically get a follow-up email within a couple days, and that follow-up email will be a link to the certificate, a link to the documents, and also a link to the recording. And if you're watching this on demand,
tell you, Mike, I'm just going to jump in. If there's anything that you're missing or you want, our emails were at the front of this of the slideshow, and you can email us, and we'll be happy to send things along.
Thanks so much, Karen. If you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. So thanks so much, Karen and Dave, for everything you put together, including the documents. I know everyone's going to appreciate that. Thanks again.
Thank you.
It was our pleasure. Thanks so much.
And thanks to everyone for joining us tonight. We hope to see you back online real soon. Have a great night.